everyone hear me okay? Alright, so thanks for sticking around. Like Simon said, this is the last talk, and this is really different. So hopefully we can learn a little bit about how we do testing and how we use the the goal of this presentation is to go through all the different things that we do to test our SSL, TLS, and crypto library. What we do, and maybe it'll be useful in your project, or if you have questions. We're always looking to improve our testing as well. My name is Chris Conlon. I'm a software engineer with Wolfssl. I started with Wolfssl when we were only 3 people, and I live in Bozeman, Montana, over in the U.S. I wear a lot of different hats. My main role is software engineering, but I also head up our support team. I help a little bit with our testing team. I do some pre-sales and marketing. We have a stand out here, so we've been visiting with open source users for the last day. So I really have a fun time. If you need to reach me, you can reach out over email at chris@wolfssl.com. I'm also on Twitter. I can't guarantee how responsive I'll be, but email is definitely the best way. So how many of you have heard about Wolfssl or know what we do? So about a third of you probably. So we make an SSL, TLS, and crypto implementation. We wrote ours from scratch, from the ground up. It's written in C, and it's roughly 10 years old now. It supports up to TLS 1.2, DTLS 1.2. It's very optimized, so low resource use. The full footprint size is about 60 kilobytes. And it works very well in both embedded all the way up to like a large-scale server environment. We're currently, still a fairly small company. We have 19 people, but we've been growing every year. And we're based in 4 countries. Our headquarters is in Seattle, Washington. I'm in Bozeman, Montana. We've got a guy in Portland, Oregon. Some guys in California, 1 guy in Tokyo, and 1 guy in Brazil. And a contractor that kind of works for us part-time in France. So today's outline, I'll just go through a quick introduction and go into the types of testing that we do. Hopefully we'll have some time at the end for you guys to ask questions. So why is testing important? And especially in security software. So the security software is really one of the core pieces of your application. Especially if you're dealing with user data, you're trying to secure data that's in transit, secure data that's at rest. And so you really need to make sure you want your users to trust your application. And indirectly, they're trusting security that you're using in your application. So it helps to know that it's well tested, well vetted, it's widely used, and there's a lot of eyes looking at the code base. And one thing that we've learned is, being open source security is very helpful. That means any of you guys can pull up our GitHub account, look at our code base. We can have universities look at us, different security teams. So with SSL, it's providing data integrity, confidentiality, and authentication. So we try to test all these different pieces throughout the next slides, types of testing. These are the types that we're going to cover today. So we have unit testing, cyberspeed testing, algorithm testing, and static analysis, detecting memory errors, doing interop testing with other implementations, peer review, third-party testing, some fuzz testing, CI, and then just going through kind of our nightly test cycle. So first up is unit testing. So the goal of unit testing for us is to provide a quality tested API to our end users. And so unit testing aims to test the most granular function. And for us in a library, that granularity is an API function. And so we have unit tests for our SSL layer and crypto. We wrote our own test framework that doesn't have any external dependencies on a third-party package, so it makes it more portable across platforms. And it's run automatically, well, somewhat automatically, every time the user runs a make test or make check. We run, among other things, our unit tests. And so if you download our code, run make check, you'll see that begin API tests and end API tests. also run as part of that same executable as our Cypher suite tests. So the goal of this is to test all the Cypher suites that we support in our library. And the Cypher suite, if you're not familiar with that, it's a representation of algorithms and protocols that are used in making an SSL or TLS connection. And so it verifies the suite's going to work as expected. Here's some examples of Cypher suite strings. They're kind of small, but I'll put the slides up afterwards that you guys can download and look at this. And in our normal build, we have 196 Cypher suite tests that we do. If you enable DTLS, which is datagram TLS, that bumps up to 300. And so that's 49 and 75 suites, respectively, being tested. And this is testing against ourselves, so we spin up our example client and test it against our example server, which is going to look something like this. You'll notice that first we test the regular Cypher suite, then we test that in non-blocking mode, so using non-blocking I/O. We test it with client authentication turned off, and then lastly we test it with both those, client auth turned off and in non-blocking mode. And so each 4 of these are run for all the Cypher suites that we test. So somewhat related to Cypher suite testing is algorithm testing. So you want to make sure the algorithms are implemented correctly and that they're working properly. And so we have a couple things that we do for this. The first thing we have is a Wolfssl test suite. So Wolfssl is our crypto library. And what this does is run through all of our algorithms that we have implemented. And it has a set of input vectors and matching output vectors. So these are NIST vectors. And the other thing that we do is we recently went through FIPS certification, which is like a stamp of approval certification for a crypto library. And with that, there's a whole bunch of test vectors that come with that. So on a regular basis, we run all those vectors through the library as well. So again, this is verifying the correctness of the implementation of an algorithm. And it's also helpful when porting, because we can port to a new platform, run these tests, and make sure the crypto is working on a new device or a new platform. Just to give you an idea of what those look like, so on the left we have our Wolfssl test. On the right is a little snippet of our FIPS test harness, where you're reading in test vectors that come from files and outputting them to a response file. The next thing we do is static analysis. So the goal of this is to find bugs somewhat automatically by using static analysis tools. And this is going to follow different code paths. So code paths that our developers may not have tested when they were working on a feature. It'll test less used or less frequently used code paths. And to do this, we use the Covariety scan tool, the Klang's scan build. And we recently started using the Facebook Infer tool, which is a new static analysis tool being put out by Facebook. So memory errors is another big thing, especially in a SSL or crypto library. You don't want a seg fault to happen, or your program to crash when it's doing some security operation, making a handshake or sending data across a TLS connection. So it's important that we vet these out, and we use an algorithm to do that, the memcheck tool. So this can detect accessing memory that you shouldn't be accessing, incorrectly freeing memory, finding memory leaks, etc. The next category we do is interop testing. So we want to make sure we tested the algorithms. It doesn't necessarily test the correctness or the protocol implementation. So they still protocols, the TLS protocols. And some of those RFCs are somewhat vague or hard to read, and they can be interpreted differently by different implementers. So doing interop testing is important because your application is, applications in the wild are most likely not talking to the same implementation on each side. OpenSSL might be talking to a Wolfssl, or a LibreSSL might be talking to a boring SSL. So we do regular interop testing with the implementations I've listed over here, which include OpenSSL, boring SSL, SSL, GNU TLS, and Embed TLS, which used to be Polar SSL. So if we're not testing against you, we'd like to be interop testing if you have a crypto implementation. or an SSL implementation, we'd like to throw you into our test suite. So if you fall into that category, please come up and talk to us sometime today or tomorrow. So verifying the correctness of algorithms and cipher suites is important. But another way to stop bugs getting into the main code branch is through peer review. So the more eyes that you have looking at code, the better the code is in the end. And what we use is a fork and then pull request system. So all of our code is on GitHub. All of our developers in the development cycle have to fork our code into their own fork, do their development on a feature or bug fix, and then submit a pull request back to our master. And then that'll be assigned to someone independent of them who hasn't even worked on that feature or fix yet. And that person's responsible for testing it, reviewing it, and then they merge it back into the master branch after that. So having two sets of eyes really reduces the amount of bugs that end up in the master branch that then we don't have to find originals later on. And it's done on every commit that comes into our master branch. Next up is third-party testing. This is different than interop testing, where this is external parties like security researchers or customer or user labs that are analyzing and looking at our code base. So we've had teams from Google and Intel look at us. I think Intel's gone through it almost line by line. We have other customers and users who analyze it. We've done our FIPS testing, which is an external review. And we pretty regularly have university researchers and people working on theses or doctorate work look at us and submit comments and feedback back. And being open source really makes this easy because anybody can look at it and analyze it and give their suggestions or feedback. The next category, so we added this, I believe, roughly 2 years ago. We started fuzz testing with FOSDEM. And so fuzz testing tests guided but random inputs to the library, and with a hope to make the library crash and find a bug or a point that could potentially be a vulnerability if released into the wild. And to do this, we use a couple different tools that we developed in conjunction with one that Google has contributed back to us partly. And the first one is Wolfssl. This is an in-memory fuzzer. So it spins up a client and a server, and it communicates over memory buffers. So it doesn't actually go over a TCP connection at all. And it fuzzes all the public-facing buffers that you would have at a TLS level. So hash buffers, IO buffers, etc. The advantage of the in-memory tester is that it's very fast. So last numbers I heard, it was fuzzing 4 trillion combinations, every couple months, I believe. The second one we have is a network fuzzer. So this introduces the TCP into the mix. So instead of using memory buffers, it actually goes over a TCP IP link. The advantage of this is that you can test it with other implementations. So you can fuzz us on one side, having another implementation on the other. The disadvantage is that it's a little bit slower since using a socket is slower than just running over a memory buffer. So we do continuous integration testing. We use Jenkins for this, which is a pretty cool package, and we like the work those guys have been doing. So on each pull request, we do continuous integration. We run our FIPS build. We do a known configurations test, which includes common configurations, user configurations, and more frequently used ones. We run our Valgrind memcheck tests, and we do our static analysis with scan build. So all these things are run on the pull request before it gets assigned to another developer to review. And then lastly, our nightly test cycle is again done by Jenkins. So this runs tests that are more extended, that we don't want to take up time during the day, or that might be going too long to do on each pull request. And so with these, we again do our known configurations test. We have an extended build options for tests, so we use AutoConf to build and configure our library. And we have, our list of options is ever growing. So we have a set of those that we test with multiple compilers and multiple platforms. Compilers, we tested GCC, Clang, and Intel's ICC. And I believe our platforms, we test the desktop platforms at the moment, so OS X, Linux, and Windows platform. And then we also do extended fuzz testing overnight. So just to kind of recap, the testing that we do, we went through unit testings, cipher suite testing, algorithm testing for implementation correctness, static analysis, detecting memory errors, interop testing with those implementations that we listed, peer review, third-party testing, fuzz testing, CI, and test cycle. We just wanted to give you guys a glimpse into what we do. We have a goal of being the most well-tested SSL and TLS library available to you, and we think that makes it better for everyone. Makes it better for open source users as well as people who are using it in a commercial project. We're a company, and we do provide commercial support to paid users, but we offer free support to open source projects. So if you want, if you're looking to add SSL or TLS to your project, you can get in touch with us, and we'll support you through that process for free. You just have to send us an email at support@wolfssl.com, and that reaches the whole team, and we assign it to one of our engineers and work you through any issues or problems that might come up. And again, if we're not interop testing with you, please contact us. We'd like to throw your tool into our testing cycle and testing framework. And with that, I guess I'll open it up. Does anyone have questions about Wolfssl or about how we do testing?
Thank you, Chris. Questions? Hey, we talked a little bit earlier, but our conversation was cut off. So I'm curious. Most of the fuzzy testing seems to be at the implementation level. It's at the almost like integration testy level. Have you considered doing property-based testing on units of your code instead of one single fuzz? For example, using conjecture or quick check libraries against individual units of your code?
Yeah, so doing it more at the function level versus like the external buffers that are public facing. Yeah, I think that is one thing that is on our list. We'd like to do more testing. Usually it comes down to a matter of time, allocating resources to it, knocking everything out at a time. But thanks for bringing it up. If it's not there, I'll make sure we do add the charges.
Do you have some workload testing? Some loading testing?
So like stress testing. We don't have any stress testing in-house, but we have customers that are using Wolfssl in very intense high production environments that have multiple hundreds of thousands of connections coming in. We have users that are processing hundreds of thousands of hours like web traffic a day using Wolfssl. So at the moment we've relied on those types of customers to give us feedback on how we perform under heavy loads.
Since you've applying such a big range of tests, which strategy has been shown to be most successful to find bugs for you?
Yeah, that's a good question. So which strategy has been most successful at finding bugs? The fuzz testing hashed out quite a few, especially when we first implemented it. There were a lot of, so let's say you have a buffer and you randomly mutate one byte in it, so that it becomes like a corrupt TLS record or some kind of handshake record. And that found several areas, I would say like on the order of like 4 to 8 fairly important things, where it would cause the library to crash. But on a daily basis, like the continuous integration testing and those tests catch quite a few things. Especially given that we support so many different platforms. Out of the box, we support probably like upwards of 20 to 30 different operating systems. And the developer might not have all of those in mind when he's adding a feature for one specific platform. Like like say somebody's working in a Mac OS X environment, they're adding a new feature, they may not think to test it in like Linux 64 and 32 and Windows. Oh, and this Freescale Kinetis device over here. So it helps to have that in place, from what I've seen.
So you said you're doing these interop tests with other TLS implementations. So if the other implementation behaves correctly, these are more or less good cases. So you also bad case tests of TLS, for example, if the other side doesn't behave like the protocol specifies.
So that's a good question. Right now, we're only trying to make a valid connection to the other end. So we haven't purposefully injected errors into that connection. With the exception of the network fuzzer, if we put another implementation on the other side. We don't currently have the network fuzzer set up to automatically test against other implementations. So for that, we've had to manually fire up, like, say, new TLS on one side and lists on the other. But that's something that would be helpful to add for a test cycle.
You said that you are more than happy to get other implementations and submit them to your tests. Do you do the reverse thing? Submitting your code to other people's or other implementations and tests?
Yeah, we would be very open to anyone accepting our code to put in their own test framework.
But is it part of your process for bug checking?
For us
Like,
to someone else.
are you just open to the idea that someone else would do it, or do you actually do it?
We haven't traditionally done it ourselves, so we haven't gone and put us in someone else's test framework.
I'm also doing some speed comparison tests. So if your church implementation is faster after some bug's been fixed or whatever, or hashing functions if they're quitting.
So, performance test. So we do test like before and after something that we think is going to affect the performance. So like say we add a new hardware crypto support, and we're definitely going to test it before and after and get the delta performance there. Or if we add a new assembly optimization, we'll test it on several different platforms that would support that and measure the performance gain, or hopefully not the performance loss in that case. We don't automatically test performance against other implementations, but I can tell you our user base continuously asks us, how do you perform against implementation X or Y? And we do have some things that we can send them in those cases, but it's more like a benchmark that we run at one time. It's somewhat recent, but not like instantaneous result. That's a great way too for automated performance testing.